My name's Paul Tarr and I'm from the University of Manchester in the UK, and I'd like to talk about understanding and reducing crater counting errors. Firstly, apologies for not being with you in person as my partner is due for an operation tomorrow, so I've had to stay here in the UK for that. But hopefully we'll have time at the end to have some questions via Skype. Now, the first thing you'll see is I put a plot right up front in the introduction. I've done this because this particular plot I think nicely illustrates the problem that we're tackling. Now, the data that went into this plot was taken from the Robbins et al. Paper, the variability of crater identifications in Icarus. And what we have is, along the x-axis, we have a count of craters within a particular region, and on the y-axis we have the errors on those counts. Now, the yellow triangles show a 1 standard deviation error computed from, I believe it's table 1 in the Icarus paper, Robbins Icarus paper, and the red diamonds are the conventional Poisson assumed errors, which has been standard within crater counting for many decades now, which is simply the square roots of the counted quantity. Now, we can clearly see that the theoretical errors based on Poisson assumptions are far smaller than the actual errors observed in the Robbins paper, and clearly that's a bit of a problem. One of the most useful things about crater counts is comparing them across different regions. Now, if there are large errors, it means there have to be really significantly large differences in crater counts in different regions in order to say any difference is observed with any confidence. So these errors up in the 20% plus region really can limit the applicability of crater counts for comparative studies. So we've seen the size of the errors observed in practice, but where did they come from? Well, there are at least 3 sources of error. The first one is the natural variations in cratering events, which is the typical model assumed, which is Poisson. And this is a perfectly reasonable model for the errors, as impact events are discrete, rare events happening in continuous time, and that is exactly what Poisson statistics is designed to model. And that gives us the conventional square root n error bars. But there's more than that. There are false positives. People and machines count craters that are not really there, ambiguous features. There are also false negatives, where people or machines fail to spot a real crater, therefore it becomes a missing crater in the data sets. Now, only Poisson variation is usually shown in error bars on size frequency distributions. In fact, it's part of many standard software packages. The software will put the Poisson error bars on for you. And that does not account for the highly variable human repeatability, and it doesn't account for the false detection prone automated methods either. So what we need is a comprehensive error model and some standardized crater definitions to try to alleviate these issues. So I have here a rather simple model to explain where the errors in crater counts come from. Now, we'll start by assuming that there is a true yet unknown number of craters, of real genuine craters that are in a particular region. But within that region, there's also an unknown number of ambiguous features that could be counted to become false craters. Now, some fraction of both of those groups will be counted. So if ND is the total number of counted craters within a given diameter range, then this is equal to nt times pt, which is the total number of true craters that is counted. And we add to that nfpf, which is the total number of false craters counted. Now, the only time we can trust nd to be the true number of craters and then apply simple Poisson errors is the case where pt, the efficiency of counting the true craters, is up at 100%. But also, simultaneously, pf, the efficiency of counting false craters, that needs to be down at 0%. Now, in practice, pt is never 100% and pf is never 0%, and the variability in these efficiency terms can account for the larger than Poisson errors seen in practice. So what I'll hopefully show during this presentation is that the NF-PF terms can almost be completely removed as a source of variation, and we do that using a technique called linear Poisson models, which is a non-parametric mixture modelling method that has been used previously on Mars terrain analysis. And I'll also show that whilst the NT-PT term cannot be corrected perfectly, we can at least attempt to estimate what the PT efficiency term is, and we approach that using binomial statistics. Let's begin with estimating false positives. Let's assume that we have a data set and every single genuine crater is present within that data set, so the PT term, in other words, is up at 100%. Let's assume that. But let's also imagine that there are false positives in there are contaminations, because the PF term is not at 0. Now, the way we approach this is to use a technique known as linear Poisson models, and I'll talk about this in more detail in the next slide, but briefly, we create template images of craters and we look at the response that template has when matched to true and false craters and learn the indicative distribution of match scores. Linear Poisson models, it's a machine learning approach, but unlike most machine learning approaches like support vector machines and random forest and boosting and so on, linear Poisson models provide a predictive error theory which will give us not only estimates of quantities at different classes within distributions, but also measurement error covariances on those quantities, and ultimately it's those error covariances that will be the basis of error bars, and that's what we want. We want reliable error bars taking into account known sources of uncertainty, and in this particular case eliminating one source of uncertainty, which is the false craters. So in more detail, what we did was we took Apollo 17 Moonzoo annotations and we divided them into true and false examples based upon a definition of what is a real crater. And we constructed mean grey level templates using a couple of things. We used the raw grey levels. If you average many of the true craters together, you end up with a crater that looks not too dissimilar to the template image in the top right hand corner. Alternatively, another type of template that can be used, and what we tried, is based on derivatives, based on gradients. So we look at the differences in adjacent pixel values, and because this can be done in both the X and Y direction, it's a composite template, and that is shown below the other templates on the right hand side. Now, once we have the templates, we need some mechanism allowing us to compare those templates to examples of craters in another image. Now there are lots of match scores that could be used. We chose to use a dot product and a mean square error based score. So we have two different match scores, two different types of templates. And we can plot the distribution of match scores for these different templates. And at the bottom of this slide we have a couple of plots showing those distributions. So we can see that now that these are for the dot product match score. On the left we have the grey level template being used, and on the right we have the derivative template being used. And the true craters show up in the blue regions and the false craters in the red regions. So we can see objectively there is a difference between the two classes of craters, and this objective difference can be seen in the distribution of match scores, and we can use this information to make the estimate of false negatives. So going into even more detail, the way the linear Poisson models work is, given a set of training data such as examples of false craters and examples of true craters, we construct a linear model composed of probability mass functions weighted by some weighting quantities. In this case it's the QK terms in this likelihood formulation on the first line, and we maximize this likelihood in order to estimate what the QK, the quantity terms, will be in new data sets. Now each class of feature is denoted as one of the K's. So one K could be the false positives, and another K could be the true positives. The HX is the histogram of match scores, and the PX given K terms, they are the probability mass functions that the linear Poisson models have learned and uses to approximate the data distribution seen from the template match scores. Now, once we've estimated the QK terms, the quantities of these different classes of feature, we'd also like to know what the errors are on those quantities, and that's achieved using error propagation. Very briefly, error propagation works by looking at how small changes in input data affect changes in summary outputs. Now the details are far more complicated than I can present on this slide, and the linear Poisson models paper, the original paper and also the Martian terrain analysis paper, go into more detail explaining this, and there are references to those at the end. Now, to test that this mechanism works for estimating false positives, we used bootstrap resampling on Moonzoo data. So we used a subset for training, and then we resampled the data, adding a small amount of noise to make sure that we are not overtrained, and we repeatedly made measurements of how many false positives versus true positives were in the bootstrapped resamples. Now, given that our primary goal is to understand errors, we have evaluated this by looking at the errors we would predict on the number of true and false craters versus the actual spread of estimates of true and false craters from the bootstrap resampling. Now, if the predictions worked, the ratio of the two should be close to unity, and that is what the plot on the left hand side shows. Now, this was based on using a combination of the gradient match scores, and so the dot product match scores and the MSE match scores in combination with different templates, the mean grade template and the gradient templates, and all the results are plotted on the same plot here. And along the x-axis we have the ratio of training to testing data used, so the number of training examples versus the amount of data we then subsequently analysed, and the y-axis shows the ratio of the observed to the predicted errors, and as we can see across the range, we do have approximately equal. Well, the errors are approximately correct, given that we have a close to flat line at unity. So this means that our predicted errors are representative of the actual errors when we look at the real data. Now, in terms of how big these errors really are, the plot on the right hand side shows for the different combinations of templates and match scores, we can get errors down to within percentage level, and I can tell you that this is approaching the limits of Poisson errors, so we're getting close to the desired Poisson errors, which is just the natural perturbations in crater counts. And as the quantity of data goes up, the errors proportionally come down. The best performing arrangement is when we use the dot product match scores with the gradient templates, and the reason why we believe this is because the gradient images are more invariant to local illumination changes, and also the dot product match score that we have used is also less sensitive to global illumination changes. So what does this actually mean in real terms? Well, assuming that there are negligible missing craters, so false negatives are not necessarily a problem. If that's the case, then this technique can be used to correct counts for contamination, thereby reducing the overall error. And the inclusion of an error theory within linear Poisson models can also provide predictive error bars on those corrected quantities. Now, even if a universally accepted crater definition isn't available, if there's no consensus, then individual researchers can still apply their own definitions in order to normalize a third-party set of annotations to match their own. So this might be appropriate if there is a highly complete yet contaminated dataset from, say, a citizen science project, and a researcher would like to make those datasets comparable to their own. This could be an option. So in terms of the original error model, the original crater counting model on one of the early slides, what we've essentially done is we've removed the NFPF terms, leaving only the NT-PT terms. Now the PT term, if that is not 100%, we still have the problem of estimating the number of missing craters, and that's what we'll take a look at next. Now, the issue of missing data can be addressed using repeatability data. Now, if a crater counter is given 2 opportunities to count every crater within a given region, some of those craters will be counted only once, and hopefully the majority of those craters will be counted twice. Now, the ratio of craters counted once to those counted twice can be used to estimate the binomial efficiency of the crater counting, and that can be done using the simple formula in the right corner. Now, we've computed this for 8 different regions of the Apollo 17 sites using both undergraduates and Roberto, our expert crater counter, and we have computed these, and the results are on the next slide. Now we can see across the 8 test regions the binomial success probability of crater detection for both expert and undergraduate is approximately the same, and we're typically looking at between 70 to 85% markup efficiency in one pass of the data. So to wrap things up, we have a false positive contamination quantification method, which can account for the contamination, the false craters that are erroneously included in crater counts. But for it to operate, it requires a standard definition of what it means to be a crater. Alternatively, the method could be used to normalize counts to individual researchers' definitions. So whilst that will mean that it's still difficult to compare different researchers' counts to one another, if you have a large data set, a contaminated data set, but is otherwise complete, individual researchers can normalize those data sets in line with their own definitions to make the third-party counts compatible with their own. Now, we've successfully applied this at the Apollo 17 site with the help of Moon Zoo data, and we've used the linear Poisson models to not only remove the quantities of false craters, but also provide error bars through its predictive error theory. However, the Moon Zoo data does also suffer from missing data. Now, false negative calibration, dealing with missing data, now that is still difficult, as by definition an unknown missing data, if it's missing, it is unknown. But we can make some reasonable assumptions, say using binomial approximations. We can compute the markup efficiencies, and we've done this for experts and undergraduates. However, that does assume that there is a binomial process going on, and the lack of absolute ground truth means this is a difficult one to test. So we have a few references. The linear Poisson models papers explain the method in more detail, and also the Martian paper, how they've been applied to Martian image analysis. There are also a couple of Moon Zoo papers that will hopefully be coming out soon, so keep an eye out for those. You can find more information at tinavision.net, and also please do visit the Moon Zoo website, www.moonzoo.org. Thank you very much for your time.